Okay, a quick video to look at examples where you're given multiple chemical equations and therefore you need to be able to work through the multiple equations to figure out what's the relevant mole ratio for your stoichiometric calculations. So this is usually related to a titration question, stoichiometry question. The examples below are from something called the Winkler Method that involves 3 reactions. Only one of them is the actual titration reaction, the last one, where you actually perform the titration, add something of known concentration to figure out an unknown concentration. The first couple have to do with different chemicals and different chemical reactions that take place when you add chemicals to water. The goal of the Winkler method is to determine the concentration of dissolved oxygen that's in a given sample of water. And so oxygen or any gas really that's dissolved in water can be quite finicky, can leave depending on what you do to the water. If you change the temperature, for example, it's very sensitive to those changes. So the idea is you take your sample of water and you add, in this case, these manganese 2+ ions. That fixes the oxygen in place. It locks it in as magnesium oxide, magnesium 4 oxide. And then that magnesium oxide can be further reacted. And at that point, actually, the oxygen ends up in water. But what we care about is that that manganese oxide reacts and forms some iodine, because then we can test for iodine with a titration here with S2O32-, which is something that's called thiosulfate. So this titration between iodine and thiosulfate is a very common titration that we can use. Usually we use a starch indicator along with it. Starch is something that turns very dark blue in the presence of I2, but it doesn't have a color in the presence of I-. So we can see a color change once we've used up all the iodine here. Okay, but what matters is the thing we're trying to find out about. We're trying to find out the concentration of O2. That's what we don't know, and it's what we're trying to find. And the thing that we're actually titrating is down here, thiosulfate down in this equation. So this is an example where the two things that we're trying to use in our calculations are not in the same chemical equation. So we're going to have to figure out how to find a mole ratio between them. It's actually easier than you might think. So where I would start, and let me erase some of this other stuff just to make it a little bit more clear. So I would start down here in the last equation. The thiosulfate connects with the iodine, and I can pretty clearly see that that's a 2-to-1 ratio just from their coefficients. And I've chosen the iodine because iodine is something that's in the third reaction, but it's also in the second reaction. So it's sort of the link between my second and third reactions. So then what I'm going to do is I want to find the ratio between iodine and MnO2. Now the reason why I chose MnO2 is because MnO2, manganese, we would call that manganese 4 oxide because of the oxidation state on the manganese. So I'm going to choose this substance because it's the link between the first and the second equation. And then finally, I've got the ratio between the oxygen and the manganese. Now, okay, still doesn't seem very simple here. What I would do is I would go through and I would multiply the equations as necessary so that the coefficients are the same on these linking chemicals. So what do I mean by that? I can see that the iodine has a coefficient of 1 and 1 in equations 2 and 3. So I don't need to do anything to that right now. But the MnO2 has a coefficient of 2 in the first equation, and it only has a coefficient of 1 in the second equation. So that's where it gets a little bit confusing. So what I would do is I would add a coefficient of 2 here. Now I'm not just adding it, I'm multiplying this whole equation by 2. If I do that, it's still going to be balanced, but now the coefficients are going to line up between equation 1 and equation 2, so they'll match. Now, yeah, I can go through it one by one. I can double everything if I want to be really careful. But really, the only ones I care about are the iodine and the manganese oxide. So now I've made this a 2 in front of the MnO2, and I did that to match what it looked like in the first equation. That had the knock-on effect of making the iodine have a coefficient of 2. So now I have to also adjust my final equation. So if there's a 2I2 in equation number 2, I'm going to put a 2 in front of this I2 as well. Now, how do I do that? I'm not just adding it to iodine, I'm adding it to everything in this equation. I'm doubling all the coefficients so that it's still balanced, but the coefficients are the same between the two different equations. Okay, now what I can see is that all the equations are going to nicely link together, and I'm going to be able to see my mole ratio. So let me use a new color. So 1 oxygen will yield 2 manganese oxide. 2 manganese oxide yields 2 iodine. And then 2 iodine yields 4 thiosulfate. So by going through and making all these coefficients the same in these chemicals that link them, I end up with the overall ratio that is 1 oxygen for every 4 thiosulfates that react. So remember, in this one, the actual titration that we do is this last equation. So we're going to actually start out by figuring out the moles of thiosulfate, the moles of this stuff. And then what all that work that we just did was to figure out the mole ratio, and that's what we're going to use in step 2. In step 2 of this calculation, we use that mole ratio, where we take the moles of thiosulfate and we put it on top of 4, because there's 4 thiosulfates for every 1 O2. So we'll take the moles of thiosulfate that we get in the first part of the question, and we'll use that to solve for the moles of oxygen. So when you have multiple chemical equations and you need to find out about something, in the first equation, using something in the last equation, you have to find the chemicals that link them. So in this case, we had iodine linked the third and the second equation, and MnO2 linked the second and the first equation. And then my suggestion, there is another way to do this, but my suggestion is go through and make sure all of the coefficients match. And you do that by multiplying equations as needed, and then you can clearly see the coefficients and the ratio at the end. 1 to 4 when we get done with that one. So that's how you deal with multiple chemical equations and determining a mole ratio. This is relevant not very often, but there are a couple of titrations where you first carry out a couple of reactions to create something, in this case iodine, that we can then test for with the titration in the final reaction. So you've got your prep reactions, which contain the thing you're testing for, in this case oxygen, and then you have the titration reaction, which is the actual analytical test at the end.